I'm going to do a simple power series example. So we're going to solve second differential of y plus y equals 0. And I'm going to call this equation 1. Right. So we're going to assume that y is in the form of c0 plus c1x plus c2x squared plus c3x cubed, and so on. And this is equal to the sum of when n equals 0 up to infinity of cn x to the n. Okay, we know this because when n starts at 0, we've got c0 x to the 0, which just gives us c0. And then when n equals 1, we have c1 x to the 1, and that gives us c1x, and so on. Okay, what we want to do now is differentiate each term in y to give us this first differential of y dash. And then so c0 just disappears because it's a constant, so the second term goes to c1, and then it's plus 2 c2x plus 3 c3x squared, and so on. Right, and this is equal to the sum of n equals 1 up to infinity of n cn x to the n minus 1. Right, now what we want to do is differentiate each term here to give us the second differential of y. And this is equal, so c1 disappears, so we get 2c2 plus 2 times 3, which is 6, c3 x, and so on, and this is equal to the sum of n equal to 2, starts there at c2, up to infinity of n minus 1, sorry, I have to go down here, times by cn x n minus 2. Okay, so but what we want to be able to compare the second differential of y with y. So to make this easier, we're going to rewrite this y dash dash as the sum of n equals 0 up to infinity of n plus 2 n plus 1 cn plus 2 x to the n. And we're going to call that equation 4, and then just back up here, we're going to call that equation 2, just because we need to refer to them in a minute. So we're going to substitute both equations 2 and 4 into the original formula. So to do that, we have the y dash dash, so that's equal to the sum of n equals 0 up to infinity of n plus 2, n plus 1, cn plus 2 x to the n. Okay, and then we want the y part, so up here, so that's just plus n equals 0 up to infinity of cn x to the n. Okay, and we can rewrite this as the sum when n equals 0 up to infinity of n plus 2, n plus 1, cn plus 2 plus cn, all times by x to the n, and that's equal to 0. So if two power series are equal, then the corresponding coefficients must be equal. So therefore, the coefficients of x to the n in equation 5, which we're going to call this here, must be 0. Okay, so we can write this as n plus 2, n plus 1, cn plus 2 plus cn equals 0, and cn plus 2 equals minus cn over n plus 1, n plus 2, n equal to 0, 1, 2, 3, and so on. So we're going to call this equation 6. And this is called the recursion relation. If C0 and C1 are known, this equation allows us to determine the remaining coefficients recursively by putting n equal to 0, 1, 2, 3 in succession. Right, so putting n equal to 0, we get C2 is equal to minus C0 over 1 times 2. Putting n equal to 1 is the same as C3 equals minus C1 over 2 times 3. Putting n equal to 2, we get C4 is equal to minus C2 over 3 times 4, which is the same as C0 over 1 times 2 times 3 times 4. We know that as 4 factorial, so that is equal to C0 over 4 factorial. Okay, when we put n equal to 3, we get C5 equals minus C3 over 4 times 5, which is equal to C1 over 2 times 3 times 4 times 5, which is C1 over 5 factorial. Putting n equal to 4, we get C6 is equal to minus C4 over 5 times 6, and that's equal to minus C0 over 4 factorial 5 times 6, which is equal to minus C0 over 6 factorial. Now finally we want to put n equal to 5, which is C7, which is equal to minus C5 over 6 times 7, which is equal to minus C1 over 5 factorial times by 6 times by 7, which goes to minus C1 over 7 factorial. Right, by now we see a pattern. So for the even coefficients, C2m equals minus 1 to the n, C0 over 2n factorial. And then for odd coefficients, we see C2n plus 1 is equal to minus 1 to the n, C1 over 2n plus 1 factorial. Right, if we put all these back into the equation 2, which was when y equals C0 plus C1x and so on, we get C0 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus dot, dot, dot. At the end we have the minus 1 to the n x to the 2n plus 1 over right, I'm going to rewrite this bit, sorry, I've made a mistake there. Right, so the y equals C0 plus C1 x dot 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 is equal to C0 is equal to C0 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial and plus the bit we found out, minus 1 to the n x to the 2n over 2n factorial plus C1 that's over 4 factorial, sorry, that's over 3 factorial, that's over 5 factorial, minus x to the 7 over 7 factorial, and then we have minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Okay, so we've got this now, and this is all equal to what we want from the beginning. C0, the sum of n equals 0 up to infinity of minus 1 to the n, x to the 2n over 2n factorial plus C1 n equals 0 to infinity of minus 1, okay, times by, just come down here, x to the 2n plus 1 over 2n plus 1 factorial, the end.